So good afternoon, everyone, and welcome to this SPS Physics Seminar. So today we have Dr. Satyaki Kar from AKPC Mahavidyalaya, and Dr. Satyaki Kar did his BSc Physics from Presidency College in the year 2000 and his MSc from JNU in the year 2002. And then he went on to do his MS in Physics from Florida State University in 2004 and finished his PhD from Florida State University in 2010. And after that, he was an assistant professor at University of North Florida from 2010 to 2012. And then he moved to India and he was a research associate at SNBN CBS Kolkata, visiting scientist at SINP Kolkata, senior research associate at IACS Kolkata, and postdoc fellow at IOT Bhubaneswar from 2012 to 2019. And from 2019, he is at AKPC Mahavidyalaya, where he's working as an assistant professor. And Dr. Satyaki Kar is a condensed matter theorist, and he works on a lot of topics, including quantum magnetism, non-equilibrium dynamics, ITC, and topological semimeters. So today, I'm going to talk about quantum oscillations in topological nodal line semimeters. So with that, I'll hand it to you.
Thank you so much, Dr. Sharma, for the detailed introduction. I would first like to say thanks to School of Basic Sciences, IIT Mandi, particularly the wonderful host, Dr. C.S. Jadhav, and also S.K. Pandey. So for having me here and giving me this opportunity to present my talk here. Okay, but let me just right away start the talk. The title of the talk is Quantum Oscillation in Topological Nodal Line Semimeters, and basically I'll go over these two recent papers that I worked on. So the presentation is on that, and so this is me, Satyaki Kar, and this is my college, as already Dr. Sharma told you, and I also have a picture of my college for you. That's like a 70 or 80 kilometers away from Kolkata. That's a good place to visit. But anyway, so I'll just go right away to the topic. So basically, the contents of the talk is I'll just briefly mention what is quantum oscillation, and then what is nodal line semimeters and the connection between these two. Then I will start from the simple continuum model of the nodal line semimeter. There I'll discuss the Fermi surfaces, the Onsager relations, and then two different scenarios I'll be talking about. First, when the magnetic field B is perpendicular to the nodal plane, and the second one is when this is in the nodal plane. And in those two cases, I'll just discuss we'll have some discussion on density of states, reduced effective masses, Zeeman contribution, etc. Also, in the second case, when the magnetic field is parallel to the nodal plane, they will see the magnetic oscillations is topologically non-trivial. So we'll talk a little bit of that also, and then finally we'll conclude. So when you talk about the quantum oscillation, first what we have to think is that what we have to do is that we are talking about motion in the magnetic field in a 2D or 3D systems, and also the magnetic field is varying. So what is the output of that? So we'll start very simply from the 2D electron gas. So if you have electron gas in a plane and a magnetic field in the perpendicular direction, then we know that there are these cyclotron loops that occurs for the electrons. They have these orbits, and it has a frequency omega c is EB over m. And then picture wise, we can have a cartoon like that. So in the bulk of the system, we have these cyclotron orbits. Is everything fine? Okay.
So let's say you can see.
You can see it, I think, and then that's fine.
Well, that's fine, no problem. So we have in this cartoon, we have in the bulk, we have this cyclotron orbits, but at the edges, we have these skipping orbits because the edge comes in the way, so it cannot complete the full orbit, and then we have an edge current there. So now this is the actual the problem, but if you want to see that much more deeper sense, you have to go to the momentum space and then see what is happening. So this is my Hamiltonian. It's a free particle problem. So it's p square over 2m, and the wave function is the plane wave functions, and this is the energy eigenvalues. And picture-wise, this is my momentum space. The k points, the allowed k points, you can see they are equally distributed. The distances between them depending on the finite sizes of the sample. And then these red circles are the concentric circles of the equi-energy lines. Now, if you apply the magnetic field in the particular directions, we have this PL substitution. A here, P becomes P minus EA. A is the magnetic vector potential. And then if you work on with this new Hamiltonian, with that, you ultimately get a Hamiltonian like that, like a linear harmonic oscillator Hamiltonian in the y direction. And then its energy we know, this is like n plus half h cos omega c being the same omega c, we just cyclotron frequency we just mentioned before. Now here, this y naught over here, this is px over eb. So this is not a constant because px is varying. So you have a number of them. So that's why this this n index, which is here the lambda level index, has huge degeneracy. So that is the problem. And then if you again look at the k space picture, the allowed k values now completely reoriented. They are now these concentric circles will be there, which correspond to different lambda level indexes, and the k points will be on the circumference of these different circles being equi-spaced among themselves. So this is the Landau quantization. Now, if you have a third dimension, third direction in a 3D electron gas, those cyclotron loops they advance forward in the third direction. And this is the physical space picture. If you want to go to the momentum space, you have to have these semi-classical equations, and then that leads to a picture of this kind, which says that now we have these 2D electron loops like that, but now these loops doesn't stay in one single plane. They can be in different parallel planes designated by different kz values. Now this kz is the new parameter now because we're considering third dimension. This is the new energy expression. So now we have a picture like this, and this tube kind of thing, where which correspond to one particular n value, is called the Landau tube. This circle over here, this is a cut of the Fermi sphere. So this portion of the tube that you can see here they are the occupied state. So electrons can be there. The Landau tube can be extended above or below from there also, but according to the zero temperature picture, there will be no occupied states there. Okay. So and then now that was what I just said only for one Landau level. Because we have different n values, we have different Landau tubes, and then this is within the Fermi sphere. This is the actual picture. We have different Landau tubes, and they are all oriented along this magnetic field direction. And then if you change now magnetic field, if you keep on increasing the magnetic field, all these individual Landau tubes get more and more fatter. And at one point of time, it crosses this Fermi sphere, and there will be no more occupied states at that moment. So that is the picture. And now if you can take a look at these two pictures over here, here we are actually considering an energy shell between E and E plus DE, and trying to find what are the electrons within that energy shell in a single Landau tube. So for here, according to this picture, this shaded region over here, this one and this one, those are the regions where the electrons have the energy within that range. So the density of state will be proportional to the volume of that region. Now you can have a special situation where this extremal area of this shell, energy shell, becomes same as the Landau tube area of cross section. In that case, you will not get these two separate shaded region. You will get a central shaded region, which is much larger in size, so which have much volume. So the density of states will be much higher. So this is the situation where we see a peak in the density of state. Now, if we now keep on changing the energy, keeping magnetic field fixed, or if we keep energy fixed and change my magnetic field, in either situations, this kind of scenario will occur periodically. So if you plot them in the density of states here, I'm plotting the density of state here in this plot. You can see this is the energy axis. These peaks in density of states will appear periodically. So here the picture is shown for DOS versus energy. We can have a similar picture where your Fermi energy is fixed. Now you're changing the magnetic field. There also you will get oscillation like that, and that is the oscillation we call quantum oscillations, where the density of state is showing some oscillation when I'm changing the magnetic field. Now it can be shown that if we plot this oscillation not with B but with inverse of B, we can see a constant period of that. That is the quantum oscillation period. So then we can just take a picture of that thing. This is basically taken from, I think, Ashcroft and Marmin's book. So here this is on some compound, and the magnetoresistance is plotted, which depends on the density of state. And this is magnetic field here in this x-axis. You can see as the magnetic field strength is increased, the period of quantum oscillation increases more and more, but their period is not constant. But if you plot the same thing in the inset, see this, the same thing is plotted now with 1 by B. There you can see the period is actually constant. So that is the thing, that is the feature of the quantum oscillation. If you plot with 1 by B, you can get a constant periodicity, and that can be backed up by your mathematical formulations also. This is actually showing the area of cross section of the Landau tube, and that can also be written from the Onsager relations. Only the difference is that here we have a half factor, here we have a gamma factor. This is more general because in many different cases gamma can be different from half. That's why this is more general. This is the Onsager relation, and this is the area of cross section for the nth Landau tube. Now, when that density of state peak occurs, that has to be equal to the extremal surface area of the Fermi sphere, and that you can say is something like SE as it written here. So now when I'm changing my magnetic field, successive Landau tubes actually changing their shapes, and then one by one they're at some point of time they are having their area cross section same as the extremal area cross section and giving density of state peaks. So if you want to calculate the period of that, you just have to consider two consecutive Landau tubes. When they do that, and then after some calculation, you will see the period will be some constant like this. So this is the constant period of the quantum oscillations. So this is for the 3D electron gas, simple 3D electron gas. And then if we want to talk about the nodal and semi-metal, first this is the simple picture for energy band diagram. Depending for conduction band and valence band, if you don't have gap, we have metal. If you have gap, depending on the size, you can have insulator or semiconductor. And for semi-metals, you have gaplessness only for some few K values, not for the other ones. So this is very special because only for few K values we have gaplessness. So the conductivity is not as enormous as in the metal case. But the thing is that this touching of the conduction and valence band, if that somehow occurs linearly, then the effective mass becomes 0 at the crossing point and the mobility becomes huge. So that changes things very dramatically, and you can get very interesting physics. So that is actually what we have in various topological systems, also in our nodal and semi-metal systems. So here you can see this picture. This is a picture of a 2D system, just like graphene, where this conduction band and valence band are touching linearly. So because they are touching linearly, they have a constant slope. So that means they have a constant electronic velocity. So you can use Dirac equation to describe such system, and our Dirac Hamiltonian will look like that. Vf being the electronic velocity, the Fermi velocity. Sigma is the pseudo-spin matrix, which basically denotes the orbital freedom, conduction band and valence band, and P is the momentum. And the same thing if we can have in the 3D, where in the 3D Brillouin zone, this linear touching of conduction band and valence band occurs. Those actually occurs in pairs. So those points are called wild points, and this material is called wild semi-metal. Now things can so happen that this doesn't touch like into discrete points, but rather touch in a closed line of loops in a Brillouin zone, and then you will get this nodal line semi-metals. So that's what the topic of today's presentation. Now if you say a little bit more on nodal line semi-metals, this nodal loop that we just said, this is actually very much robust, because by some local deformation you cannot completely wipe it out. From our knowledge of nearly free electron theory, we know that if there are two bands which comes very close to each other, there is band repulsion. and then we deal with such problems with degenerate perturbation theory to get an estimate of the gap there. But then if there is some extra symmetry attached to these bands, we cannot do that. There is no hybridization, and this gaplessness is protected, and such kind of things happen in various cases also in nodal line semimetals. Now the symmetries that comes into picture in these cases are like mirror reflection symmetry, inversion symmetry, time reversal symmetry, spin rotation symmetry, etc. like that. And there are some examples of the nodal line semimetals. Now this robustness of this existence of nodal loop that we just mentioned, this is topological. So that's a topological non-local order parameter attached to that. So basically we have to go to momentum space and consider several mathematical constructs like Berry connection, Berry curvature, Berry phases, where this u is the electronic wave function, and then suppose this is my nodal loop in the Brillouin zone, this black ellipse, and then we have to find some electronic pathways, and along that closed line of loop, you have to calculate this Berry phase. It turns out if that the value of Berry phase for this closed line of loops of electronic pathways becomes non-zero, that is an indication that it has some non-trivial topology. And in this case, if such electronic pathways rings through that nodal loop, then we get non-zero values for the Berry phases, and we always can find such kind of electronic pathways in nodal line semimetals. So that's why my nodal line semimetal is a topologically non-trivial system. Now, experimentally, if we want to witness the topological non-triviality of such systems, generally what is done is angular resolved perturbation spectroscopy is used to determine that, because in other topological systems, just like Weyl semimetal, the surfaces also show some topological behavior. But particularly for nodal line semimetal, that doesn't happen. They have drumhead surface states, which are always most of the time not topologically protected. So RPS doesn't help much here. But you can use quantum oscillation measurement. That way, with that, we can very easily calculate the Berry phases, non-trivial Berry phases, and see whether this is zero or non-zero. And then once you get this is non-zero, you can say, okay, this is topologically non-trivial. So this is the main connection between quantum oscillation and nodal line semimetal, that this can help very easily determine whether this system is topologically non-trivial or not. Okay, so I'll just skip this slide. And so that is the introduction of nodal line semimetal and quantum oscillation. Now we'll just talk about the simple models we just worked on. So this is the simple toy model of nodal line semimetal, continuum Hamiltonian. This is a 2x2 Hamiltonian. These sigmas are the pseudo-spin matrices that denotes the orbital degrees of freedom, one conduction band and one valence band. And from there you can see, if you can get these energy expressions from there, this energy expression epsilon becomes 0 when my kz is 0 and my k perpendicular square is 2m star delta over h cross square. So this is basically showing that energy will be 0 in the kx ky plane along the circle. That is the nodal loop in this problem. And then here, if you just plug the magnetic field in the perpendicular direction, then again the Hamiltonian gets modified, and then you can, in the Landau level basis, you can get a nice expression for the Hamiltonian, and this is the expression for the energy eigenvalues. This is plus and minus branches because of this conduction band and valence band. Now here we also need to see how the Fermi surfaces look like. If my energy is 0, then the Fermi surface is basically
n can take value 0 in there.
Yeah. If
So can you
okay.
N here, right? N can it be 0?
N can be 0. I don't see any special.
So in Weyl semimetal you get 0. Nodal lines Weyl semimetals you get this like there is 1 0 chiral line.
I know for Weyl semimetal this n equals to 0 we have some chiral states. But then here I actually don't see that here. Like n equals to 0 doesn't look like very special.
Yeah. Okay. Yeah.
So now here among the Fermi surfaces, if my energy is 0, then the Fermi surface basically is the same as the nodal loop. It falls on top of the nodal loop. But if my energy is positive, then we have some torus Fermi surfaces which basically covers the nodal loop. So the nodal loop is sitting inside this torus. And then if I increase the energy, the torus become more and more fat, and the inside hole becomes smaller and smaller. And at one point of time, the inside hole will be no more there. We'll have a drum-shaped Fermi surface, so which is a clear change in topology. Now, if we want to study the quantum oscillation in such system, let's first consider this torus-shaped Fermi surface, where this dashed line, dashed circle you can see here. This is the nodal loop which is sitting inside. Now, for quantum oscillation, we have to first consider one direction of the magnetic field. Let's say the magnetic field first is in this direction, along the z direction. So now we have to pause and think what we are trying to do. We are basically trying to calculate the period of quantum oscillations. So for any oscillations, in order to find the period, we have to first consider one particular phase of that, and then let's see how often that phase repeats. So that particular phase that we generally here consider is where the density of state becomes maximum, the peak comes. Now that comes when this extremal area of cross section comes into picture. Like the Landau tubes crosses the Fermi surfaces extremally. So that can be accessed only for some particular range of the parameters. Like here, if my magnetic field is in this direction, the extremal surfaces can be accessed only if I put kz equals 0. So only in the kz equals to 0, we have these two yellow circles. You can see these are the extremal electronic pathways. One is minimum, another is maximum. Both are extremal. So there only we can have those extremal area of extremal electronic orbit. So for quantum oscillation purposes, we only consider those planes. Like when my magnetic field is in z direction, we consider kz equals 0 plane. When my magnetic field is in the x direction, we consider kx equals 0 plane, because there we find this external area of cross sections. Now, one thing you can see here right away, that if my electrons go along these yellow circles, they never actually ring through the nodal loop sitting here. So that's why the Berry phase, if we calculate corresponding to this closed pathway, will get 0. So that actually amounts to trivial magnetic oscillations. So if my magnetic field is in the z direction, all my magnetic oscillations are trivial. But if it is on the x direction, we can have these blue colored electronic extremal pathways. And if my electron goes along that, and if I calculate this Berry phase, because that rings through this nodal loop sitting over here, we will get non-zero Berry phases, and that amounts to non-trivial magnetic oscillations. And then that can also be backed by these equations, just like earlier what we discussed. Now here in this Onsager relation, we have this gamma factor we discussed before. This gamma actually related to this Berry phase gamma b in this fashion. So if somehow we can calculate this gamma, we can readily calculate gamma b and then see whether this is 0 or non-zero, and that will tell us the topological nature of the oscillations. So as we said, so this is the general expression for the dispersion. So to access only the extremal area of cross section, we keep kz equals 0. So it gets simplified to this expression, the energy expression, and then this is plotted here, the dispersions. So we get a pair of them for each n values, and so these are the different dispersion lines plotted with magnetic field. And then these mu1, mu2, mu3 are different energy, different Fermi energies. For each of them, you can see they cut these dispersions in discrete points corresponding to different B values. Those are the B values where the Landau tube cross sections become same as the extremal area of cross section. And then if we collect all of them branch-wise, not to confuse with plus and minus branches, branch-wise, if we collect all of them and then plot them in a 1 by B versus N diagram, which is called the Landau fan diagram, you'll see they are aligned linearly. And then if you draw that line, and then you'll see they will all meet at a particular point. So they have a common N intersect. and that can also be seen from this relation, which is also a different way of writing these Onsager relations. So this, wherever they meet, knowing that point, we can get the value of gamma. So here it will show that value of gamma is half. And then once we get this gamma, we can, from here, we can get gamma B, which is the Berry phase, and it turns out to be 0 in this case, because as we already said, that if my magnetic field is in the Z direction, my gamma B should be 0. So now then the next thing to consider, we have to consider the magnetic field, which is parallel to X direction. But before that, we will just say a few, one more thing, that we were talking about these different mu lines, mu1, mu2, mu3, those are constant, but when you are studying quantum oscillations, actually these mu's are not constant, they are also doing some oscillations. And then we have to measure that also, we have to quantify that also, because that's also one important feature of this problem. So to measure those, we can start from thermodynamic potential, omega, which has this expression. We are only considering, so far we are considering only zero temperature formalism, so this TES factor doesn't matter here. And then from there, we can take a derivative with respect to chemical potential that will give us the number of electrons. So we do that, we get the value of omega, we take the derivative and get the value of n. So this is n, which is in terms of B and mu and some other things. Now, if we change my B, because we are considering it's a closed system, that n should be constant, n should not change. So to make n constant, my mu also has to change. So numerically, you can calculate these changes of mu, and this is plotted here. This is 1 by P, this is Fermi energy. And then you can see some oscillations over here, and then the oscillations amplitudes are increasing more and more as my magnetic field is increasing, just like quantum oscillations. And because we are plotting here with 1 by B, we can kind of see here the periodicity is a constant. If you would have plotted it with B, you would see that this is no way like that. So this is one thing, and then other than this mu, we can also calculate other things like parallel magnetization, which is basically the derivative of omega with respect to magnetic field. This is the expression, and then this is one plot for different mu values. So from here also we can see that this magnetization is having some quantum oscillations in it, which is growing more and more if my B is large. And
I have a question. Can I ask? Like, for example, this quantum oscillations, you see in metals only, right? Because wherever there is no, so suppose you have a material which is having finite dose at the Fermi level, but the electrons are localized at the Fermi level. So in those, but when you take the resistivity, it shows insulating behavior. So those kind of systems, do you see as quantum oscillations?
So you are saying it has finite DOS?
DOS at the Fermi level, but the electrons are localized at the Fermi level.
Okay.
For whatever reasons it is, and so essentially it becomes insulating, like a disorder kind of Sanderson kind of thing. So suppose if it is it becomes insulating because of that. So those kinds of systems, does it show quantum oscillations? Are you aware
I don't know.
Okay.
But then okay, it's something I should of course take a look and then.
Yeah. Okay, thank you. Yeah.
Okay, thanks. Okay, so so basically in these magnetization plots, we can see this oscillation as well as some average behavior. The average behavior you can see, as my B is very small, this goes to 0, and then as I am increasing my B, this is going to some positive value. It's increasing, which it should be here. And then apart from that average behavior, we have these oscillations. Now that oscillations we can study separately, and that has been done. Basically, we have this Lipschitz-Koservich formula, which basically gives an expression for such oscillations, delta M, which is we just subtract the average part, and whatever is left is delta M. And then he computed that can be written as some just simple sinusoidal oscillating function with some prefactors. Some 3 reduction factors are here. One is due to temperature, another is due to finite relaxation time, another is due to some spin reduction factors. So, and then this F is the fundamental quantum oscillation frequency. So now if my system have more than one fundamental oscillation frequencies, we have a sum of all of such terms like that. Now in our problem, so far what we have used from our simple model, we can see that because there are two extremal surfaces, that actually amounts to two different fundamental frequencies. So we'll get two fundamental frequencies from there, and there will be two terms in my delta M expression. Now experimentally, if you can take a look, this is a plot from this paper, who worked on ZR SIS, which is a nodal line semi-metal system, and they took the magnetization data, and then from the FFT spectrum.
Is it not true that we have only one extremal surfaces for one field direction?
No, two. There are two yellow circles you can see.
So this is when you're along the x direction.
No, when you are along the Z, this is the Z direction.
When the field is upward, and this is a kz plane.
This is my KZ plane.
Yeah.
And then two extremum. One is minimum, another is maximum.
Okay.
So one is inside one, another is outside one.
Okay.
And correspondingly,
Okay,
there are
this
two
is-
apes.
this is-
Yeah. So, but experimentally also you can see in the FFT spectrum, there are two peaks. They call this alpha pocket and beta pocket, just like two Fermi pockets. And then this F alpha and F beta peaks they can find in the FFT amplitudes, which is incompatible with our model. Of course, they also get this higher harmonics 2F alphas, but we are not going to talk about that here in our theoretical calculations. So far so good. We can compare things at least qualitatively, that we are supposed to get two peaks. Theoretical also we can see that from our Fermi sphere, Fermi surface. But then we also have to consider Zeeman term. If we consider the Zeeman contribution in our Hamiltonian, we have to add a term like that. If we add a term like that and then do our calculation, we will see my Fermi surface will be like two toruses, one inside another one, because the two spin degrees of freedom has to be now treated separately. So we have a Fermi surface like that, and then if you take a cut, we will get four Fermi surface, four extremal area cross section, and that's why four fundamental frequencies. Again, they are not constant because they have this B, which is magnetic field B over here. So it turns out this is different than what we should get, we see experimentally. But turns out if you plug those things in this LK formula over here, in this summation of all these four terms, and then do some simple algebraic steps, actually we get back the previous apes what we had with some extra prefactor. So we are still good even with my Zeeman contribution in my calculation. We get the whatever previously we were getting 2F values, this time also we get the same F values with some additional extra factors. So with even Zeeman term also, the models are doing something, giving some results which is compatible with the experimental findings. And then we have to, here some plots are there in order to understand how important these Zeeman contribution terms are. So basically here we have plotted, we have varied the effective masses. The effective masses in this system, experimentally it has been seen, the effective masses are very small. They are not the same as the free electronic masses. They are like 0.1 of free electronic masses and sometimes even smaller than that. So we have shown some variation of that, and then with that, how the Landau levels behave like that. And with that also, we have kept the Zeeman contribution to see how they compare. Now, when we put the Zeeman contribution term here, which is basically this one, this G mu B by 2, G being the Landau G factor, which is usually we take 2, but here we used 38 because we are actually following this paper. And experimentally, how they calculate this G, they basically first they get their M star, and then from there, this is their delta M data, and then they only see the Zeeman splitting when the magnetic field is very large. Like here, these are two Zeeman splitted peak. So corresponding to those two, they have this B plus and B minus. From there, they use this formula to get the value of G, which turns out to be 38.
What is this system?
This is your ZR SIS semi-metal system. So we use that value and try to see how they compare with the different Landau level dispersions. And then here, again the dispersions are shown where we have varied the magnetic field. Also different both G equals to 2 and G equals to 38 are considered, just to get a feel how this Zeeman term is changing things. Okay, so then we can also calculate the density of states. We just start from the very basic definition of density of states, which is basically sum over this delta function of E minus the dispersion energies with some prefactor, which is basically coming from the Landau level degeneracies. And then here numerically we calculate that, and this has been plotted here. From the trend you can see it looks like 3D density of states, but other than these regular peaks, which are basically coming because of this different Landau states. Now there are two plots over here. One is black and one is red. In one I didn't consider the Zeeman term. In the other one I did consider that, but they don't see much difference. The reason is that the Landau level spacing turns out to be the same as the Zeeman splitting. So even if we consider the Zeeman term and then we get the splitting, the splitted peak actually falls on top of the next peak which was already there. So we don't see that here. But then if we change my M star value, if we consider a small M star value, which usually can be seen in these compounds, then this matching is no more there. Then you can very clearly see these Zeeman splitted peaks in the density of states. So this is something to notice in the density of states. Okay, so that is something to talk about when the magnetic field is in the perpendicular direction. If my magnetic field in the plane, nodal plane, let's say in the x direction, then what happens? Then the problem is a little bit more trickier, because here the kx ky symmetry of the problem is lost because my magnetic field is in the x direction. So, but still, what we do is that we just write the Hamiltonian with the magnetic field after the PL substitution. This is the expression, and then to get the energy, we just do it numerically using exact diagonalization. So this is one plot is shown here, and then again we have to consider those. Means we have to only access the extremal area of cross section. So this time, just like last time we considered kz equals 0, this time we will consider kx equals 0, px equals 0. That is also compatible with these dispersion plots. So we in this problem we have to keep kx equals 0. Now putting kx equals 0, we again go back to the b equals to 0 case. There the low energy the minima, there are two minima at these 2 points, which are like direct points because there are all these linear crossings. And then about these two minima, we have the low energy Hamiltonian, which is like an anisotropic direct Hamiltonian, shown like that. And then when we again add the magnetic field along the x direction, we can write the Hamiltonian in this fashion, and then that can be conveniently rewritten in this way. We'll come back to that later. But numerically, whatever we have, we can diagonalize and get the spectra. From the spectra, you can see the main feature of the spectra is that there are, when my magnetic field is very small, they are doubly degenerate. At some point of time, this double degeneracy get lost, and then we have these non-degenerate bands coming from each of these lines. And this is there both in the positive and negative energies. Now, if we want to understand this thing theoretically, what we have to do, what is generally done, is that basically we square this Hamiltonian. When you square this Hamiltonian, it turns out it becomes a Hamiltonian which is like a nonlinear harmonic oscillator Hamiltonian, where there is a kinetic energy term and there is a potential energy term. This is the potential energy term, and this potential energy term looks like this is not the actual Hamiltonian. This is the one we get when we square it. So this Hamiltonian, we have this double well potential. These two wells, if they are very far apart, which occurs when my magnetic field is very small, if they are very far apart, we can treat them independently. And about these two minima, there are two linear harmonic oscillators, and they have their own energies whose frequencies are same. So we have two sets of harmonic oscillator energies, and because their frequencies are same, there is energy matches. So there is the double degeneracy is coming from there at low B values. But then as I'm increasing my B, the gap between them, these two potential well, is reducing. So those two problems are no more independent. and those degeneracy, what the problem was enjoying so far, is no more there, and that degeneracy is lost. So at some point of time, we get this thing to split out like this fashion. And then also you can get an expression from there. So basically what we worked on the square data, and then worked on that Hamiltonian. So whatever energy we get, we have to take a square root. When you do that, we get an energy expression of this fashion. So you can see here, this energy is proportional to square root of B as well as square root of N, which now here we can call the lambda level index. So things are not linear here. Now again, just like previous time, topological aspect you can see for these problems also. This is the dispersion again. So if we consider some low energy, you can get a, from the lambda fine diagrams, you can get a gamma, and then from there get a gamma B, which indicates a non-zero value. So non-zero Berry phases. But if my energy is large, we again get zero Berry phases. Better to take a look at this picture. So these are the two Fermi surfaces. This is the Fermi surface at low energy. It's a torus, and this is a high energy Fermi surface, which is a drum-shaped Fermi surface. And then if you take this kx equal to 0 cut, you get these cyclotron orbits. So for low energy, we get these two small orbits, and inside these orbits, we have these two direct points we just mentioned before. And then if we want to calculate the Berry phase along either of these cyclotron orbits, we will get a plus pi or minus pi Berry phase. So that's why this oscillation is non-trivial. But if we do the same thing here, this time my cyclotron orbit is a big one, and both the direct points are inside it. So if you want to calculate the Berry phase, the result will be plus pi minus pi equals 0. So basically, this is actually giving me trivial oscillations.
Why its energy is compared with this M not with the mass?
Oh, sorry. Actually, this is delta. Sorry,
This is delta, right?
This is delta
0, right?
Yeah. I should have changed that. And then again, here we have, this is the dispersion plots, what we have just shown before.
And
And
what is this delta? Let me say this is delta.
delta
We are talking
means
of
in the
delta,
Hamiltonian
right?
there is one term, right? Actually, two
Yeah,
notations.
right, here is the term. Yeah, there is the term. Delta plus minus.
Yeah, this is the delta.
Delta.
Yeah, this is the delta. See?
Gap at gamma point.
Yeah, this is the delta.
Okay, okay, that small gap that is.
That is actually creating the radius of the nodal loop.
Mhm. Radius.
Of the nodal loop, it has a radius that is proportional to delta or square root of delta. From there you can see that. So so here basically we are considering the Zeeman term also, and then with Zeeman term added, you can see the dispersions are splitted like that. And then as we have already discussed, this region, this small region which is highlighted here, this is the region which is the topological region. Like there in the low B regime, we get these topological oscillations. Now if we reduce the effective mass, the spectra changes, the spectra becomes more broad like that, but that makes that topological regime become more small. So it gets shrink. It becomes a small region. It might have my very small M-star values. But we can undo that. We can, if we consider very small V value, which is the electronic velocity, the Fermi velocity of the electrons in the Z direction. If we follow the equations, you can see that if we consider a small V value, then again we can undo this effect and then make this topological region becomes more stretched, which you want. We always want to have non-trivial oscillations because that is more interesting to consider. And then this is the density of low energy density of states. Unlike the previous case, we don't have these peaks appearing at very regular levels, and then also we have at zero energy we have a huge non-zero value for the density of states, which was also not there in the previous case when B was perpendicular. But then if I reduce my M star to 1 to 0.1 value, then that zero energy peak shifts to some positive energies, and all the other small peaks what we are having, they shift further into higher energy side, that we can see here. And then also this red and black ones are the red ones are the one when we consider the Zeeman splitting also. If we can zoom in, you can see there is Zeeman splitting in each all of this. And then this is just the last slide. So this is basically because when my magnetic field in the x direction, we can access two different topologies, like non-trivial as well as trivial, and that can be accessed if I change my magnetic field. So we can choose a range of B that includes that transition point, and then we can periodically drive it in this fashion so that that range repeats over and over again, so that this topological transition from trivial to non-trivial oscillations can be repeatedly accessed. So we can do that if we can choose my B carefully, and that way, first of all, those different topology regions can be accessed over and over again periodically, and then also we can have some jump electronic level transfer of the electrons from one level to another one, if we have some periodic drive like that. So this is we can work on these problems further to see how many more interesting physics we can get from there. So that is pretty much all. Basically, we talked about nodal length semimeters and quantum oscillations, and we considered the effect of Zeeman term, reduced effective masses, and we talked about the spectral feature, the topological feature. We considered the two different directions of the magnetic field and the features of these two different ones. In the case where magnetic field is in the x direction, parallel in the nodal plane, we can have some topological oscillations also. So we talked about topological transitions in such systems also. And then there we also mentioned that we can consider some periodic driving for the magnetic field that will that help us getting some interband transitions, and then from there we can study many other things also in future. So that is all, and thank you so much for listening. And I should acknowledge GST CRB because of their funding. This is the grant number. And then also I should thank Anupam Shah, who was a student of mine as a project fellow, who did some of the calculations. Those are shown here. So that's all. Thank you so much. And this is a link. You can take a look. Some part of this this kind of talk is there. Thanks so much.
Thank you very much. So now we can have questions.
To go back to your Landau Venn diagram, very first slides, not this.
This one?
Yes. So this one. Suppose when you say n equal to 0, we start counting that this is the first Landau level, second Landau level, right? From where does this counting start? Because as you see, we can get the many number of the lines corresponding to V1, V2, right? So many. So which one we should take as a new one? So like look at this left diagram.
Yeah.
So if I took at where is my n equal to 1, which one I am taking as n equal to 1?
Oh, so basically here you have to plug in the value of n, 1, 2, whatever you want, and then see what the energy is like. You have to follow these lines, dispersion lines. That will tell you which.
So which side is your n? N point. Which one is your n equal to 0 point? Or first Landau level point? In this.
I think. Okay, let me.
If we go to the lower b value,
Okay,
then the b can be very, very small.
See the slope. What is the slope? The slope is, if you do the slope, the
Yes.
slope will be n plus half e h plus by n, right? So for n equals to 0, it has least slope. So it should be this one. So these two should be n equals to 0. And then n equals to 1, n equals to 2, like that.
Right, so here this is cutting at B equal to something 7 Tesla,
Yeah,
right?
yes.
Somewhere 7 or 8 Tesla.
Yeah.
Is it for this system only or because it can be very large? Because in some system, for measuring, suppose I do this measurement for 40 Tesla, I will start seeing the oscillation.
Okay.
Experimentally,
Yeah.
I just keep on seeing the oscillation to the higher field.
Yes.
So then where would my n be? N equal to 0.
Okay. See, from this calculation, you can see the maximum value of this cut is coming for n equal to 0, right? So if you are taking quantum oscillations at 40.
Because this is correct, as you are saying theoretically, this formula will give this. But when I will do the experiment, I'll start seeing oscillation from a lower value of the field, and I will keep on getting until the light.
Yeah, because they have their own parameters.
Yes.
So in your problem, whenever you are doing, so you have to get the actual parameters for your problem. So your delta may be different, and then because of all those things, there will be not 7 Tesla, there will be some different number. So if you are getting quantum oscillations at 40 Tesla, should be this cut should be around those values, I think.
But experimentally, when I'm doing this, I do not find really very nice region that where should start counting the end of it. So that's a worry. Maybe I'll discuss you further.
Okay. Yeah, with parameters, this thing will change. I think we have to find the correct parameter for particular different experiment. Is there any other questions?
So, can you go to that effective mass and value of G?
Oh. Which one?
So let us suppose somebody wants to verify this model is correct.
Oh.
Yeah.
Okay.
So what is the meaning of effective mass here? In what
Effective mass means the effective mass has its definitions, like it's like I think inverse of del 2 E del K square. So
but effective mass is a very dicey kind of thing. So if you look at the people define different context and different context, different effective mass.
Of course, means this is like
of a state effective mass, which is looked in terms of the specific.
Yeah,
then you have a cyclotron related with the cyclotron. There is another effective mass.
Yeah. No, here
what?
Here effective mass means just like, as far as I remember, is the definition is 1 over del 2 E del K square. Now that K square you can do K perpendicular square or K parallel square. That demarcation I didn't mention here. I should have. So these same stars are
in which experiment they will be able to see this signature of the effective mass, which is less than.
From the DFT calculations, right? No. From the DFT calculations, you can.
I am talking about the experiment.
Experimental
wise also. For example, so density of a static effective mass you will get from the specific. So here,
see from the alpha people they are from the alpha they take data in a different direction you may get a different.
That is there, like if you can do
that is related with the directed dispersal.
Whatever I understand,
so that is directly so
from the dispersion they calculate, right? That's what I know.
The way you are defining it is based on that. Yeah. So now let us suppose what is this G mean here? If somebody is getting very large value of the G. So in this case we are getting that.
So this is the expression
of really indicating that the some effective spins are very large.
Somehow this is basically, if you can take a look, this is in this problem, M stars are small, like the effective masses are small in this problem. As if making G larger, this is nullifying that effect. You can see if you compare two different things, Zeeman splitting and then lambda level
So
splitting.
basically telling that okay, so there is a effective quasi particle whose mass is very small, 1/10 of the
1/10 of free mass.
Electron mass, and its speed is very high.
No, it's spin half particle. This is a spin half particle.
So what this G will indicate? So what this G is indicating? Because this G is finally getting used in that expressions of the Zeeman splitting, and that is related with the basically.
Yeah. So this is
lambda G factor, which is
lambda. This is the expression of this is a B, small b you can see here.
So what physically it means?
So basically you are saying what is the physical?
Physically that is related with the okay. You have a electron. Electron is the spin half, and for electron you are getting the value of the G, which is close to 2. That is a physical meaning. So when you are equating this in that context, what it is?
So I think I don't know, but
It's not a free.
Right. So that's the thing I was asking. Because if we interpreted that okay, some quasi particle of mass 1/10 of the electron mass, and its spin is very high. So what is the value of the
no.
G
So
got?
if you go by the book, and then consider the expression for the Zeeman splitting, which is this one, B sigma 0 tau z, where B is this thing, and then you first calculating your M star. You have your data dispersions. From there, you are calculating M star. You are finding M star is very small, and then experimentally you get these plots. You get this Zeeman splitting. But then if you put G equals to 2, that doesn't add up, right? That you will end up with a Zeeman splitting which is much smaller. So to fill up that gap, I think that is the only reason they use it.
Mathematically, that is fine. Mathematically, I am not questioning.
I understand.
Let us suppose physically, if you want to interpret.
Yeah.
So then, how they will look?
Yeah. Means why G is so large? What is the physical meaning of that?
Because this G is directly related to this. That is very clear because we are still mapping interactions. You have the electron lattice interactions, and then we are still mapping that in the free electron language. So all the interactions are getting. So convert. So we interpret in that way. Okay, electron still has the effective mass of that. So that's the way. So can we interpret in that? So that's the thing I am asking. The essence of the G, different particle, it has a different way of looking at it.
No, the physical meaning is need to be understood, of course. This is they have just like mathematically concocted because that fit in everything well, and then they put it. But physically, this has to be understood, of course.
Anyway. Now go to that one. So,
in fact, when we calculate G equal to 2, right? That is also the semi-classified. No, in the beyond standard model, they do the G value and the extra they get.
This LS coupling thing, there's a big formula, right?
And so even this visualization using LS coupling and RS coupling is not a semi-classical way of treating the spins are like this, LS, and then they are doing it.
Yes, G basically it is for the free electron.
That is true.
Exactly true. There, people also keep improving.
Yeah, it's close to 2.
There is some experiment. So still people are improving, matching with the theory. Best at certain discipline.
Standard model, right?
Still people so improving experimentally. But
Yeah, that's just like you are matching the precision. You are getting better precision.
That basically comes from the
This is completely different. This is like huge from 2 to 38.
Electrode. What was that? Quantum electrode. 2.0 or something.
Are there any questions online? Time. Okay, so I think then we can then tell the students to faculty want to have discussed. So okay, so with this we thank Dr. Satyaki for a very interesting talk. So then we request the students to leave, and then if the faculty want, they can interact